a new high-speed encryption system promises to stop hackers using the next supercomputers from stealing data. Recent advances in quantum computers may soon give hackers access to machines powerful enough to crack even the toughest of standard internet security codes. This will enable them to break codes and access any online data, making all systems from medical records to bank transactions vulnerable to attack. But scientists are using the same strange properties that drive quantum computers to create hack-proof forms of quantum data encryption. The new system, developed by researchers from Ohio State University, is capable of creating and distributing encryption codes at megabit per second rates, which is 5 to 10 times faster than existing methods. And these quantum encryption techniques are secure from common attacks, even in the face of equipment flaws that could open up leaks. Professor Daniel Gauthier, an author of the study, said, "We are now likely to have a functioning quantum computer that might be able to start breaking the existing cryptographic codes in the near future." We really need to be thinking hard now of different techniques that we could use for trying to secure the internet. When we buy online, make a bank transaction or share data like medical records, ciphers called encryption keys turn their data so it cannot be read. Personal information sent over the web is first scrambled using one of these keys, and then unscrambled by the receiver using the same key. But for this system to work, both parties must have access to the same key, and it must be kept secret. Quantum key distribution, QKD, takes advantage of one of the fundamental properties of quantum mechanics. Measuring tiny bits of matter like electrons or photons automatically changes their properties to exchange keys in a way that immediately alerts both parties to the existence of a security breach. A key is created so that data can be encrypted and sent from one party to the other. Then the key to unlock that data is transmitted securely using quantum key distribution, QKD. Binary data is encoded into tiny light particles called photons. The phase, a property of photons, is altered to represent binary data at 0 or 1. The transmitter can encode these photons in two different ways, known as bases, creating 4 possible combinations. The photons are randomly encoded to create a random key and sent at precise time intervals to the receiver. The receiver detects the photons. It can detect zeros and ones, but not which base, so it randomly chooses which base it will detect and records the values and bases. Once all the information has been received, the receiver tells the transmitter which bases it detected, and the transmitter reveals which were right and wrong. the receiver rejects all wrong detection events, leaving just the correct ones. Armed with this information, it can create the key to first encrypt and subsequently decrypt or unlock the data. The system is secure because it enables eavesdroppers on the line to be detected. Any attempt to monitor the data will interfere with the photons, affecting the encoding. If there is interference, the receiver will terminate the process before the key is produced. Any attempt to monitor or interfere with the transmitted key while it's being sent will be detectable. Though QKD was first theorized in 1984 and implemented shortly thereafter, the technologies to support its wide-scale use are only now coming online. Companies in Europe now sell laser-based systems for QKD, and in a highly publicized event last summer, China used a satellite to send a quantum key to two land-based stations located 1,200 kilometers apart. But PhD candidate Nurul Tamer Islam explained the problem with many of these systems is that they can only transmit keys at relatively low rates between tens to hundreds of kilobits per second, which are too slow for most practical uses on the internet. He said, "At these rates, quantum-secure encryption systems cannot support some basic daily tasks, such as hosting an encrypted telephone call or video streaming." Like many QKD systems, Mr. Islam's key transmit uses a weakened laser to encode information on individual photons of light. But they found a way to pack more information onto each photon, making the technique faster. By adjusting the time at which the photon is released, and a property of the photon called the phase, the system can encode 2 bits of information per photon instead of 1. This trick, paired with high-speed detectors, powers the system to transmit keys 5 to 10 times faster than other methods. Prof. Gauthier said, "It was changing these additional properties of the photon that allowed us to almost double the secure key rate that we were able to obtain if we hadn't done that." In a perfect world, QKD would be perfectly secure, as any attempt to hack a key exchange would leave errors on the transmission that could be easily spotted by the receiver. But real-world implementations of QKD require imperfect equipment, and these imperfections open up leaks that hackers can exploit. The researchers carefully characterized the limitations of each piece of equipment they used. Mr. Islam said, "We wanted to identify every experimental flaw in the system and include these flaws in the theory so that we could ensure our system is secure and there is no potential side channel attack." All of this equipment, apart from the single photon detectors, exist in the telecommunications industry, and with some engineering we could probably fit the entire transmitter and receiver in a box as big as a computer CPU.